The goal of this live demonstration is to present how the decision maker can use the CUTLER platform to plan a structural flood risk reduction measure to address the problem of floods of the Bacchiglione River and its tributaries in the city of Vicenza. In the first task of inform phase, where we are, the aim is to understand the extension of the problem the decision maker has to address. So the first step is to consult the flood risk and others map of the flood risk management plan, which are presented here in a GIS interface. This color scale is related to different level of hazard. It is one for different risk classes. There are also 3 different flood scenarios, for a total of 6 maps. There are also other sub-dashboards in this task that allow to compare these maps with other useful thematic layers. For example, here we have economic layers such as the map of public exercise and commercial activities in the city. In this GIS interface, those layers are overlapped with the maps from the flood risk management plan to allow very punctual consideration. This can be done also for other kind of GIS layers, as the layer of school, buildings, the distribution of population, etc. Consult the risk maps give an idea of extension of a problem, but is not enough to plan a reduction measure. The decision maker has in fact to understand which are the hydrological, hydraulical and meteorological variables which led to floods in the past. This can be done thanks to the network of sensors of the Veneto region integrated in CUTLER. For present the sensor data, we have created into the inform phase various thematic dashboards, which presents in different way the historical recordings of the sensor. For example, here we are focusing only on 3 sensors that are relevant for the city due to their location. We are so focusing only on particular time series extracted from the entire 30 years long recordings in correspondence of the most relevant past flood events. For example, here are presented the measurement of water discharge from a sensor which is located into the Bacchiglione River on a bridge in the city center of Vicenza. Here the decision maker can understand that the most critical flood event has been the one of 2010 and that mostly the floods occurred in autumn. Here there is a similar graph for water level. For this variable, we here have measure for 3 sensors in the city. Again, the highest values are the one recorded in 2010. Finally, here we have rifle recordings from 4 sensors, one into the city area, the other 3 located upstream into the mountain part of the basin. From the graphs, the decision maker understands an important element. The high level of river in Vicenza are mostly caused by the rain, which fall into the mountain area, not directly in the city. This is crucial to plan a flood risk reduction measure. There are also some other sub-dashboards where the decision maker can access to all other sensors and to their entire recording, not fixing on particular flood events. The final element to analyze in order to have a clear picture of the issues are the results of past run of the AVA flood simulation model. This model, starting from a meteorological input, estimates water level in specific location of the modeled rivers, called river section. Why it is important to see the past result of a model if we already have sensor? That's because we have only 3 water level sensors in the city, while the spatial resolution of the model is very fine. In fact, we have more than 50 sections in the city. This allows to understand better where exactly are located the critical point, where the river overtopping occurred, which are the point labeled as those red spots here. Moreover, the dashboard includes also widgets for presenting the result in a typical way for an hydraulic model. For example, here we have a view of the most relevant river section. Here there is a view for longitudinal profile of the river. Now the decision maker has all the information to understand the extension and the nature of the problem, so we can move to the next step. Now the goal is to understand the principle of flood risk management and which approach to follow to manage the risk in Vicenza, as well as which are the possible measures to be implemented to reduce that risk. All this information are presented in the Flood Risk Management Plan of the Oriental Alpes River District, which can be consulted by the decision maker directly from the platform interface. So let's move on now on the next task. So ideally now the decision maker has chosen from the list of possible flood risk reduction measures of the plan the one most suitable for the problem. In this case we are focusing on a specific structural protection measure, the retarding Basin of Caldogno. In this dashboard are presented some information related to this measure. So now we are at the end of the inform phase. The decision maker has at his disposal the available information to understand the problem and the way to solve it. So let's move to the advice phase. Now that we have identified a risk reduction measure, the goal is to understand its expected benefit as well as the impacts. In this first task of the advice phase, this assessment is done in environmental terms. The dashboard is divided in two parts. Firstly, we have a GIS interface which compares the 6 risk and hazard maps already presented during the inform phase with the same maps but related to the expected situation in the post-operam state. In this way, the decision maker has a visual idea of expected reduction of the risk area after the implementation of the measure. Then, here we have a set of KPIs, which quantify what is shown in the map. Since there are many information there, let's focus only on a few indicators. For example, this widget here represents the percentage of surface of a municipality which falls in a certain risk class. There are a total of 4 different risk classes before and after implementation of the basin and for each of the flood scenarios provided by the flood risk management plan. Here instead we can see how we shift the distribution of the different risk classes before and after the implementation of the measures involving 3 different flood scenarios. It is relevant to notice the relative reduction of the areas at higher risk. In fact, a positive impact of the measure is not only the reduction in absolute terms of the total extension of the risk area, but also the shift of the residual risk areas from a higher risk class to a lower. Let's move on. In this task, the decision maker makes similar consideration but in socioeconomic terms. So, firstly, again, here we have the GIS interface. Now, to the risk maps ante and post-operam are compared with some of the thematic layers already presented into the inform phase, which represent a certain category of exposed elements, for example, economic activities, school, buildings, etc. In the following part of the dashboard, we have again a set of KPIs, which now quantify in different ways the GIS maps. For example, this widget shows the numbers of a certain type of exposed element in a specific class of risk, ante and post-operam, and again this is done for the 3 different flood scenarios. The final task of the advice phase is represented by Query Social Sentiment Dashboard. This is a sort of prototypal tool for AWA. In fact, currently we do not have a similar step in our decision-making process. However, as indicated by the regulation, for the most relevant policies, we establish some participative processes when citizens can express their opinions about the topic. Nevertheless, we are aware that the citizens do not limit to express their opinion in these official channels, but but they use also their personal social media accounts, so there could be a loss of information in this sense. This is the reason why we find interesting this tool, and we have decided to insert it in this policy. Although currently this is not a step in our decisional process. Now that we are at the end of the buy phase, the decision maker has all the elements to decide if the measure analyzed can address the problem outlined to the informed phase in a satisfactory way. So let's give to the platform the confirmation about this. Now the platform brings us to the monitor phase. It should be mentioned that there is a gap in between this and the previous task not supported by the platform. This gap represents some necessary procedures, like gaining all the administrative approvals or perform other bureaucratic steps, and of course the building and testing of the infrastructure itself. Dealing with the structural measures, these procedures can take quite a long time. But now let's assume that the measure has been implemented, so we have to monitor if it is working as expected in the advice phase. During the monitoring period, we have to monitor basically the same variables presented into informed phase, but referring now to the post-operam state. For example, we have quite similar dashboard for the sensor that the one presented into the informed phase, but now we are interested in the data collected by the sensor after the implementation of the basin. Respect at the informed phase, there is here an additional sub-dashboard to show the meteorological forecast. Now these data are in fact meaningful, since we are dealing with the real time. Then we have also the same panel of informed phase for consulting the flood simulation model results, but again now we are interested in the run of the model after implementation of the measure and in eventual forecast runs. Another interesting addition is this panel that allows to compare the water levels in the river estimated by the flood model with the water level measurements of the sensor. We are making this comparison for the location of the free water level sensor in Vicenza. In correspondence of each of these sensors, the model has in fact a river section defined. Why do we need this comparison? That's because we need to ensure that after the implementation of the measure, our model is still calibrated to reflect the new situation. Otherwise, we need to recalibrate its parameters, and this dashboard can help us as well. Finally, again, here we have a social sentiment query tool. Let's move to the next task. We are now at the last task, in the evaluate phase. The monitor period is ended and we have to sum up the result collected. In this case, since we are dealing with a structural flood risk reduction measure, we have to perform a long-term monitoring that can also take several years. In fact, we can evaluate properly the functioning of the basin only if at least one relevant flood event with intensity comparable to design events of a basin has occurred. So we have to adapt the monitoring period to the statistic frequency of occurrence of this kind of floods. In this case, we assume that the basin has been implemented 1 year ago and that the monitoring period is 10 years long. We have to compare the result collected in this period with the same variables collected for an equally long temporal interval, but before the implementation of the basin. An easy and rapid way to understand if the measure has worked as expected is using the concept of threshold overtopping. For each sensor which measures water level and for each river section, we can define 3 thresholds of water level. Some of these thresholds may also have a meaning for the civil protection operator, but for our purpose we are interested to see if there has been a sensible reduction of the number of thresholds exceeding in the post-operam state respect to the ante-operam. A similar result is in fact indicative that the measure worked as expected. Here, the occurrence of a threshold exceeding is expressed in number, here instead in a visual way. The ideal situation, in particular, is to have no or few third threshold exceeding the post-operant state. In fact, the third threshold is located near the top of a river embankment, so its exceeding usually means an imminent river overtopping and the start of floodings. This comparison is done both in the location of the free water level sensor in the city, both for the free river section of the flood simulation model located in the same location of the sensor. So, after this comparison, the decision maker has all the knowledge to decide if the measure works as expected or if a revision of the policy are requested.